Z-test for proportions, Chapter 9. In this example, in a random sample of n equal 100 patients, the proportion cured by a new drug, p hat, 60 over 100 or 0.6. This is taken from a larger population, of millions of potential patients. The proportion that would be cured by the new drug in the long run, represented by p, is unknown. We want to compare it to the proportion cured by the old drug. P0 is 0.51. And Part A will use the critical value method with 9% confidence to test H0, p equal 0.51. New drug has the same cure rate as the old, versus HA, p not equal 0.51. New drug has a different cure rate. So we need to check whether we can use the z-table, or if we have to use the binomial probabilities. Q0 is going to be 1 minus P0, 1 minus 0.51 is 0.49, and we need to check that n times P0 and n times Q0 are both at least 5. 100 times 0.51 is 51, which is more than 5. 100 times 0.49 is 49, which is more than 5. So they're both more than 5, so that means we can use the z-table and we don't need to use the binomial probabilities. Next up, we're going to use the z-table in reverse to get the critical values. This is a two-sided test, so half of our doubt is going to be on each side, and our level of doubt is 0.1. We said alpha is 0.1. 1.1 divided by 2 is 0.05. Our z-table only has values for the upper half of the for z between 0 and the particular z-score. So in the middle here, which is our desired confidence level, is 90%, but we need to divide that by 2 to get 0.45 and look for 4,500 in the body of the z-table. It's not there exactly, but it's about halfway in between the probabilities that correspond to that are in row 1.6, columns 4 and 5. So we'll take the average of 1.645 and 1.65 to get 1.645, and then we can compute the test statistic. It's basically a variation on the z-scores that we were computing earlier in the course. P hat minus P0, so basically the score minus the mean over the standard deviation, but that's P hat minus P0 times square root of n over square root of P0 times Q0. So it's 0.6 minus 0.51 times square root of 100 over square root of 0.51 times 0.49. That comes out to be about 1.800. That is more than a critical value, so we reject H0 with 90% confidence and conclude that the success rate of the new drug is different from that of the old drug. We can also compute a p-value. It's 2 times 0.5 minus the probability that z is between 0 and 1.80. And if we look up in row 1.8, column 0 of the z-table, that's 0.4641. Subtract from 0.5, we get 0.0359. Multiplied by 2, we get 0.0718. So if we compare our p-value to the chart below, we see that the p-value is between 0.05 and 0.1, indicating some evidence that the new drug is better than the old. Now, in testing a new drug, most likely we're primarily concerned about whether the new drug is better than the old. And for that we could do a right-tailed test. Again, we'll keep the same level of confidence. We want to test H0, p equal 0.51. New drug has the same cure rate as the old. That was the same as a hypothesis we had before, but the alternative, instead of having not equal to the symbol, will have a greater than symbol. So alternative HA, p is greater than 0.51. New drug has a better cure rate than the old. And now we want to concentrate all our doubt on one side, and now we're looking for instead of dividing by 2, we're going to look for 0.5 minus alpha, which is 0.5 minus 0.1, which is 0.4. Look for 0.4 thousand in the body of the Z table. The closest numbers are in row 1.2, columns 8 and 9. I would estimate about 1.282 because it was closer to the number that was in row 1.28 than it was to 1.29. You could just, if you want, you could just estimate 1.28 because the number was not in there exactly. And then we can compute the test statistic. It's the same test statistic we had before, 1.800. And because our test statistic is more than our upper critical value of 1.282, we reject H0 with 90% confidence and conclude that the success rate of the new drug is better than that of the old. We can also compute a p-value, so this time we don't need to multiply by 2. It's just 0.5 minus the probability that Z is between 0 and 1.80. 0.5 minus, and look in row 1.8, column 0, we get 0.4641, subtract from 0.5, you get a p-value of 0.0359. And this time the 0.03 is between 0.01 and 0.05, so this time we have moderate evidence. The sample provides moderate evidence. And that concludes this presentation.